Alright, this lesson is Unit 1, Lesson 13. Okay, it's Fluid Dynamics and Frames of Reference. So let's start with Fluid Dynamics. It's the wrong PowerPoint. There you go. Now, this is similar to fluid statics. Well, not really similar, but a lot of students who also take chemistry get a bit confused with this, because we are going to talk about things like pressure. And in chemistry, you do, well, PV equals nRT, and you learn that a gas under greater and greater and greater pressure, right? A gas that is under a smaller and smaller volume is undergoing a greater and greater pressure. And that makes common sense, right? But what we're going to be doing in this lesson is not fluid statics, it's fluid dynamics. So we don't have, say, a gas inside of a container, but maybe a gas moving through a pipe. Okay, so it's not contained, right? It's able to move in and out of our system. Okay, and when we talk about fluids, we don't just talk about, say, water or any liquids. Gases and liquids are both considered fluids. All right. There's fluid friction. So any object undergoes frictional forces. And frictional forces can be both internal or external. Right? The external frictional forces we've already studied. Well, internal frictional forces are the cohesive forces between the molecules. And we call this viscosity. So an object with high viscosity, like honey or maple syrup, has high internal resistance and doesn't flow very well. Okay, here's another term, so laminar flow. So let's say you had a pipe and you had water going through that pipe. If you have, just like this picture, each successive layer moving smoothly over top of the previous one, this is called laminar flow. However, right, if that flow becomes more irregular, right, and you'll get these little whirls called eddies, this is called turbulent flow. Right? And this can certainly happen if you have an object moving through a fluid too fast. Okay, so we do something which is called streamlining. Okay, streamlining is something you do to an object to design it to be able to go faster through a fluid. So I have two pictures here, and I'm sure you can guess which one is designed to go fast, which one is more streamlined. Okay, you can look up little videos on YouTube about like cars and wind tunnels. It's actually try and look up videos of a sports car in a wind tunnel and say the Nissan Cube in a wind tunnel, and you'll see the difference between something that is streamlined and undergoing laminar flow and something that is not and undergoing turbulent flow. That turbulent flow can also cause sort of a suction that pulls your car back. So if you have like the Nissan Cube on a highway punching through the air, that air creates these eddies behind the car and sort of pulls the car back, right? Which is why they're not very fuel efficient at higher speeds. Now this is what I was telling you at the beginning of the video that's going to confuse a lot of you who are so used to that idea where if you decrease volume, you increase pressure. This is called Bernoulli's principle. Now if you have a fluid moving through a pipe, right, and then that pipe suddenly gets smaller, what happens is the pressure actually decreases. This is very strange. You can look up, let me go to the next slide. You can look up videos like this. I do this demonstration in class, or you can look up the Venturi effect on a video. Right? But basically it looks like this. Now this is a thick pipe and a thin pipe, and we have airflow going through it. And then we have water inside of these tubes, which has these are connected to the airflow tubes, and they're open, right? They're not closed. Now initially when you have no air moving through these tubes, the water level is equal on both sides. But then when you push air going through the tube, you notice that this side with the thicker, the greater cross-sectional area, the water is pushed down more, meaning there's more pressure on this side. So the greater cross-sectional area, the greater the pressure. Now it seems counterintuitive, but you have to remember the air is moving through the system. It's not contained inside the system like it is when you in fluid statics when you study it in chemistry. Okay, so this Bernoulli principle pretty much says, so here we have a lot of fluid. This actually comes from something called the continuity principle. So let me try to explain this. Let's say you have a certain amount of fluid moving through this thick cross-sectional area in a certain time, t. It says that that same amount of fluid must move through this cross-sectional area in the same amount of time, t. Well, the only way that's going to happen is if the fluid is moving much faster through this area. And when it starts moving faster, it becomes more spread out. Right? I'm sure you can imagine, say, a bunch of cars lined up to go onto the highway. And then as they go onto the on-ramp, suddenly the distance between them increases because the car in front of them starts to move faster and faster. Right? And then you move faster, and then the car behind you, there's a bit of a delay, and then they move faster. And so suddenly all those cars which are cramped together before getting onto the on-ramp have now spread apart getting onto the highway. Same kind of idea. This is why the pressure is lower, but the speed increases. And that's Bernoulli's principle. High pressure, low speed. Low pressure, high speed. And this Bernoulli's principle actually helps to explain how a plane can fly. Now I'm going to attach a great video by Minute Physics and Veritasium that sort of goes over how a plane flies. Because you can certainly use Bernoulli's principle to explain it, but again, you can also use Newton's third law to explain it as well. And so it's a great video with lots of animations. But the gist of it is you have airflow going over a wing and under a wing. The wing is designed to bring that airflow and push it down. Newton's third law, well, if you push the air down, the air is going to push you up. But due to another effect called the Coanda effect, which sort of you create almost like a vacuum as you're pushing through the air, and the air that goes over the wing gets pulled down, and it's actually going faster than the air under the wing. If it's going faster, that means there's lower pressure. Sorry, if it's going faster, yeah, it means there's lower pressure. So there's higher pressure below the wing, lower pressure above the wing, and things tend to move in from areas of high pressure to low pressure. So that pressure difference pushes the plane up. And there's lots of examples of Bernoulli's principle. Right? I'm sure everybody has taken a water hose and put your thumb over the end of it, right? And it goes a lot faster. A vacuum, right? Same thing. Even a shower curtain, right? The water coming out of the shower is moving fast and causes the pressure inside the shower to be slightly lower than the pressure outside the shower, so the curtain gets pushed inwards. Sailing is one people don't usually tend to think of as being Bernoulli's principle. People just usually think, well, wind pushes against the sail and that pushes the boat forward, but that's not actually true. Wind goes over the sail, and just like the wing on a plane, causes areas of high and low pressure. And so I'm going to put another video by Veritasium, which is really good. Take a look at it. It's called The Physics of Sailing. If I forget to post it, look on YouTube. It's Veritasium Physics of Sailing. Okay. So take a look at that. All right, so there's no math with that lesson. We're going to move on and do frames of reference, which is the second part of this lesson. We've kind of talked a little bit about frames of reference before when we did relative velocities. So just to recap, let's say you're driving in a car on a highway and you pass somebody standing at the side of the road. The person at the side of the road will look at you and say, that person is moving 100 kilometers per hour north. But from your point of view, you'll see the person at the side of the road, and from your point of view, it looks like they're moving 100 kilometers per hour south. And if you're driving next to somebody, and you look over at the car next to you, it looks like they're not moving at all. It's all relative to a point of view. and physics makes no preference over one point of view over another. Today we're going to talk about inertial and non-inertial frames of reference. So I want you to imagine, we're going to start with a little bit of a thought experiment. I want you to imagine we're on a train. There's no windows in the room. So we're in a room on a train. There's no windows. And let's say this is a hover train, so that's moving through a vacuum tube. So there's no air resistance. There's no bumps on the tracks, and so you can't feel that sort of bumpy motion. Now, let's say you fall asleep on the train, you wake up sometime later, and you don't know if you've arrived at your destination or not, because you don't know if the train is still moving. So here's the question. Is there an experiment you can do to determine if the train is moving? You can't open the windows, you can't leave the train, you can't go ask somebody else. Just you yourself in your room. Is there an experiment you can do? Think about it. Pause the video if you want. Try to come up with an experiment. Okay, I'm going to assume everybody's back. Now, a lot of the times I get students saying, well, throw a ball up in the air. That doesn't work, does it? We talked about this when we did relative velocities. If I'm here and I'm standing still, take a ball, marker, and I throw it up, and it comes down. I can do the same thing if I'm driving in a car, if the car is moving at a constant velocity. So imagine right now I'm in a car, and I'm moving this way at 50 kilometers per hour, and I'm holding this. The marker is also moving this way at 50 kilometers per hour. And if I throw it up, I'm not applying any force in the x component. And so there's no acceleration in the x component. So as it's moving up, it's still going to be moving this way. The same velocity that I'm moving and the same velocity the car's moving. In our example, 50 kilometers per hour. It'll go up and it'll come back down. So this is not an experiment I can do to test whether or not I'm moving. And if you don't believe me, just take a pen and try it the next time you're in your car. Make sure you're not driving. Make sure someone else is driving. Okay? So I get students coming up with other ideas too. But the trick is none of them work. In fact, it's an impossible question. There is no experiment that you can do to determine whether or not you're actually moving. This is the principle of relativity. And this is when I would talk about there's really is no such thing as a rest frame, like an absolute rest frame where every other frame of reference will say, yeah, that's definitely at rest. That's not possible. Right? All I have to do is move relative to that frame, and from my point of view, it's moving. So now we have two types of frames of reference. The examples I've been doing have all been inertial frame of reference. An inertial frame of reference is one where all laws of physics, all Newtonian laws are valid. A non-inertial reference frame is when they're not valid. So what does that actually mean? A non-inertial reference frame is an accelerating reference frame. So let's go back to the idea where I take this and I throw it up in the air and it comes straight back down. But let's say I take this, I throw it up in the air. Now we're in the car, moving in this direction at 50 kilometers per hour. Okay, and then suddenly there's a red light, so we brake as it's in the air. Now I have my seatbelt on, so I come to a stop, the car comes to a stop. But what about the pen? Right? There's no force acting on the pen to come to a stop. So it's still, not only is it moving up because I've thrown it up, but it's also moving forward at 50 kilometers per hour. So from my point of view, if I'm unaware of the car's motion the entire time, it goes up and then suddenly whoop, speeds ahead forward. And I'm sitting there looking at the pen like, what just happened here? This doesn't make sense. It just completely defied the laws of physics. Okay, and this is a non-inertial frame of reference, which is an accelerating frame of reference. And there's lots of examples of non-inertial frames of reference. The biggest one is the Earth. And the Earth is rotating. And when you rotate, you're not moving at a constant velocity, even if your speed is the same. If you're moving, let me do it this way, if you're moving in a circle with the same speed, your velocity is still changing. So remember, velocity is a vector, it has a direction, and notice the direction of, in this case, my pen is constantly changing. Even though its speed stays the same. Since it's constantly changing, its velocity is changing. And so it is accelerating. And we'll talk about this, what we call centripetal acceleration in the next lesson. But for now, I just want you to have the idea that if something's moving in a circle, it's accelerating. And therefore, for this lesson, it is a non-inertial frame of reference. Okay? And the Earth is spinning. Okay? And if something tries to move forward with a great force, it's going to be pushed to the side. Why is that going to be pushed to the side? Think of it like this. How many of you have been in one of those fun houses where you have to walk across a room where the floor is spinning? You have to go straight across the room. It's not so easy, is it? You try to walk straight, but the floor, which is moving in a circle, pushes you to the side. Okay, this is what appears to be a force. That's not a real force. Right? We call it a fictitious force due to your frame of reference. Just like the pen that I throw up and then suddenly goes forward. There's no actual force that acted on the pen to push it forward. It just appeared to move forward because of my own frame of reference. And so we say this is a fictitious force. We're going to talk about specific fictitious. Sorry, I had to pause the video and now I forgot what I was talking about. So the pen that moved up, then that goes forward, there's no real force acting on the pen to do that. Right? It's specific to our frame of reference. So we call these fictitious forces. And we're going to look at some very specific fictitious forces which occur due to rotating frames of reference, which are a type of accelerating frame of reference. The first one that we looked at, which is really the cause of hurricanes, is why hurricanes move in one direction in the northern hemisphere and the other direction in the southern hemisphere. And it's because from your point of view, it's rotating in opposite directions if you just turn yourself upside down. Next slide. Okay, and we call this the Coriolis force. Okay, the Coriolis force is the force I was mentioning, where this fictitious force acts perpendicular to velocity of an object in a rotating frame of reference. I'm going to mention one other one. This is called the centrifugal force. Now tomorrow we're going to learn about the centripetal force. Very different. Centripetal force is real. This is the centrifugal force and is a fictitious force. So imagine again you're in your car and suddenly you turn to the right. It feels like your body wants to be pushed out to the left. Okay, and so you may say, oh, there's a force acting on me. There's not really a force acting on you. What's really happening is your own inertia wants to keep you going straight, but the car moves away from you to the right. And so you end up being feeling like you're pushed to the left outside of the car. Okay, but even though this feels like a real force, it's just your own inertia. Okay, and the fact that you're in this non-inertial frame of reference. So we call this the centrifugal force. And I'm going to post a video alongside this, which I found on YouTube, which is a good visualization of these circular fictitious forces. But another example, this is the last one I'm going to mention, is this is called the Foucault Pendulum. You might have seen these in huge museums, right? They're huge pendulums, sometimes going up a couple of floors in length, and they just go back and forth, back and forth. And then there's these little pegs all around in a circle, and throughout 24 hours, throughout one day, that pendulum will slowly knock down every peg in the circle. Okay, and this is actually proof that the Earth is actually rotating. right? Because the pendulum slowly is moving sideways because it's in that non-inertial rotating frame of reference. Okay, now let's try one example, which is on the back. I'm going to make my screen big. Okay, so this example, we have someone suspends a small marble from the ceiling of a school bus during an awesome physics field trip. When the bus accelerates at a constant rate forward, the string suspending the marble makes an angle of 10 degrees with the vertical. Calculate the magnitude of the acceleration of the bus. Okay, so let's think about this for a second. We have something hanging, and it gets moved back like this. So what forces are actually acting on this? If we were to draw this as a free body diagram, what forces are actually acting on it? Well, we have tension right here. So force of tension. We have gravity, of course. And we can create a coordinate system. Since we're accelerating in this direction, I'm going to make that direction positive. All right. Now I'm going to write components. And it says makes an angle of 10 degrees with the vertical. So that means this is 10 degrees. Now, if you were unaware that you were in an accelerating vehicle, let's say you're back in the train and you see that, and you have no idea you're in a train or in anything that's accelerating, this looks weird. Why does it look weird? Because, well, here we have a component of tension in Y and a component of tension in X. Now, our component of tension in Y can completely balance out the force of gravity. But there's no other forces acting in X. It means there's an unbalanced force. And if it's just hanging suspended like this is very weird. Right? There's an unbalanced force, yet it's not accelerating. So you might end up saying, oh, maybe there must be some other force in this direction. Call it whatever you want, right? Maybe you'll make a name for it and you'll start to make measurements of it and write papers about it. But it turns out you're just in a non-inertial frame of reference. It sounds easy to be able to say, oh yeah, it's obvious. You're in a non-inertial frame of reference. But it's actually really, really hard to determine if you're in a non-inertial frame of reference. You can determine it, but for many forces, which we now know are fictitious, physicists used to think they were real, right? Because just didn't realize we were in a non-inertial frame of reference, right? You make certain assumptions about the world you're in, and sometimes something that you observe is not strong enough to break those assumptions, and so you create new forces. But in this case, we know we're an accelerating vehicle, and we can actually calculate the acceleration because we have an unbalanced force here. So if we're to look at that, let's do Newton's second law. Sum of all forces in X equals mass times acceleration, and the only force we have is tension in X. And if we were to write it as a component, our tension in X is just force of tension times the sine of 10 degrees. I'll just call it, say, theta, which equals ma. I can't actually solve for a yet because that's one equation with two unknowns, tension and acceleration. They give me theta and they give me, oh no, they don't. They don't give you mass. That's three unknowns. No, I'm stuck. How am I going to solve that? It's okay to get stuck. You're going to get stuck. Leave your work, don't erase it, and try a different approach. That's what problem solving is. And that's what problem solving is always going to be. It's not ever going to be getting the answer on the first try every time. Okay? It's always going to be, it's like a maze. You go down one route, I got stuck. You go down another route, I got stuck. You go down another route, I got stuck. But every time you get stuck, don't erase that information. If you erase that information, you're going to keep going down that same wrong pathway again and again and again and again. Keep it there because it may be useful to know. Okay? So another thing we can do is we can try looking at all the forces in Y. Let's do that. Now we know they're balanced, so we're going to set it equal to 0. We made up positive, so let's have tension in Y, which would be tension cos theta minus gravity, which is mg, equals 0. Right? Let's just rearrange and so write ft cos theta equals mg. Now I can try solve for ft and substitute. That'll help a little bit, right? It'll get rid of one of my unknowns. We're still left not knowing mass or acceleration, but let's just see where it takes us. So tension equals mg over cos theta. Take that and substitute it in here. So we have tension, which is mg over cos theta times sine theta equals ma. And now look at that. Masses, you can divide both sides by mass and it goes away. The mass doesn't matter in this case. Whatever you have hanging, it's going to come to that same angle at that same acceleration. Sine over cos theta is just tan theta, so I have acceleration equal to g tan theta. Now if you just plug in your numbers, it's 10 degrees, so we'll do 9.81 times the tan of 10 degrees, or 10.0, so 1.73 meters per second squared. It's going to be forward. Alright, so that's it for that lesson, and that's actually it for chapter 2. Tomorrow we'll start chapter 3, which is all on circular motion and centripetal force, which is a real force. We're done with fake forces, okay?